So the plan is to upload the slides that you will share with us. It is recording to the Moodle platform for the students. It will be not public, password protected, for them to study the material before the examination after the school. So thank you very much for accepting the invitation to participate in our school. Let me introduce the speaker to the audience. A few words about. So this webinar will be given by Dr. Dahiya. He will speak about printed transient electronics, sustainability from Crandle-to-Grave. Few words about the speaker. He is a research associate at the Northeastern University in Boston in USA. He received his PhD from Greenman Lab in France in 2016. He has done postdoctoral work at various CNRS labs in France, including Greenman, ICMCB, and the University of Glasgow in UK. His research interests include synthesis of nanomaterials, nanofabrication, solid-state devices, energy harvesting, and printed and flexible electronics. He has published more than 70 high-impact research articles in leading journals. He has one US patent and one under review. He has written 3 book chapters in the book on technologies for printed electronics. So thank you very much for your participation, and the floor is yours. Thank you very much.
Thank you, Mr. Chair, for kind introduction and inviting me to present our group work in this summer school. So yeah, hello everyone, myself Abhishek, and today I'll introduce you to a new upcoming form of electronics, which is printed transient electronics, and how this form of electronic can bring sustainability from the start of the electronic manufacturing, where we have to select the raw materials, electronic materials, and then we have to process them, integrate them onto the flexible substrates, and after end of its life, also not going to harm the environment when they are degraded into its components. I'll begin with the introduction with the electronic skin. This is one of our core area of research from the last few years. We are working on to the development of electronic skin technology, which is kind of a subset of flexible electronics, which mimics functionality as well as morphology of biological skin. So as you see in this slide, for a comparison, qualitative comparison purpose, like biological skin have layers. For example, the top most is epidermis, which is basically to protect you from microorganisms or water-repelling properties and so on. And in the same way, we are trying to have layers in our electronic skin patches. So we have our packaging layer, which again protects from dust, moisture, and so on. And then we have a sensing layer in the middle as inspired from the skin, where we have developed a lot of flexible sensors, light sensors, temperature sensor, and so on. We can integrate into this middle layer and some actuator devices. At the end, in the bottom, we have a computational layer, which is again mimicking skin at the which goes take the signal to the brain and compute the information sensed by the sense layer in the middle. Today, my talk will be focused more on the computational layer part, how we can bring high performance or a performance which is more closer to the silicon, conventional silicon electronics, which is difficult to achieve in the novel form factors. So this performance, whenever I say high performance, includes high density integration. So you need a scaling of your devices, low power consumption, and fast computing, similar to silicon and electronics. It has many applications. So such electronics can have many applications in human-machine interaction, robotics, soft robotics, wearable computing, wherever the electronic needs to conform to irregular objects. So once, okay, we know electronics, but how we will fabricate such technology? Which approach we should follow so that we can bring sustainability during the manufacturing side of electronics? The current state of the art of flexible electronics, if I summarize here in this slide, there are three approaches we can follow. The first one is organic printed electronics, where we use organic materials and printed technologies, and we fabricate in a high throughput manner flexible electronics. The advantage of organic printed electronics that it's the materials organic, being organic, and it's very flexible. But the disadvantage is the low performance. So for example, if you see the two important factors to define the performance is the mobility of your devices and the transit frequencies the circuits are working. So here is around 2 kilohertz, which are orders of magnitude lower than the conventional silicon electronics. Then we have another form of electronic, inorganic material based, where we are using metal oxide or other inorganic, and we use printed technologies or conventional fabrication as well, and we can reach up to mobility of 10 to 40 centimeter square per volt second and transit frequency around 30 kilohertz. And the last approach is basically we use the silicon chips, we thin down to a level they become flexible around 35 to 50 micrometer. And then, of course, the performance, you keep the silicon performance, and that's similar to silicon electronics we have currently. But if we compare in terms of these conventional microfabrication and printing technologies, for instance, the CMOS, okay, the ultra-thin chips gives you the highest performance, but they are again made through a conventional microfabrication process. So this slide compares qualitative and quantitatively again the two fabrication approaches. So in terms of performance, of course, there is no comparison for the conventional electronics, where the miniaturization has reached around 3 nanometer, and we have transit frequencies in gigahertz very easily. But if you see the lower parameters, which are related to the resources you use to manufacture this electronic, and what happens after its life, they are not very promising. If you see the energy usage, water usage, land requirement, and all these factors, the printed electronics is clearly a better option. But in performance-wise, it's still way behind the conventional electronics. So how we can bring printed electronic technologies as much closer to silicon-based electronics? Today, I'm going to show some of the approaches and methods we have developed in the printers, which can print these high mobility inorganic electronic layers. And once they are processed, we can push the limit of printed electronics towards the silicon technologies. Just to give you also another solution, it's an intermediate solution, which currently the industry and academia are looking forward to bring high performance in flexible electronics. It's an heterogeneous integration, where the conventional chips, as I said, the UTCs, ultra-thin chips, they are integrated with printed technologies, and to form a heterogeneous kind of system, as you see in this schematic, where the processor, the computational part is done by the silicon-based electronics, and the rest of the devices can be fabricated through printing, and they can be integrated through either printed interconnects or conventional interconnects. some of the work we have done in this area as well, we have shown or demonstrated thinning of a wafer scale MOSFET chips, as well as we have optimized some printing, high resolution printing technologies, drop on demand, where we can form interconnects coming from the chip to the flexible pads outside. Coming back to the printed technologies and how we can achieve performance as close as to silicon technologies. These are most of the printing technologies available to realize electrode or functional layers. And for the moment, if you see in the middle, these are the ones which have been exclusively used to fabricate commercial printed devices. The advantage of these all offset gravure flexographic and screen that they have a very high volume, high throughput. They are roll-to-roll techniques, but their print resolution is quite high. So if you see 20 to 50, 50 to 200, these are the micrometer of resolution you can reach using these printers. But to scale the devices to have fast operation, you need to decrease the channel length or the gate length. And if you see these two extreme, they, for instance, reverse offset and EHD-based jet printing or extrusion particularly, they can able to print around 1 to 10 micrometer resolution lines very easily. So there is a potential coming up in printed technologies where you can scale down the channel length of your transistor and make the electronic chips faster. In terms of materials, there have been a lot of materials investigated in printed electronics. From organic metal oxide to polysilicon, carbon nanotubes, as well as inorganic 1D nanomaterials. If I summarize these, all the parameters I have taken in terms of mobility, process temperature, power consumption, stability, flexibility, and so on, inorganic 1D materials are stand out. In the near the material which can compete is CNTs, but again, CNTs, the computing architecture is ambipolar, and then the most closest to silicon is coming from inorganic 1D nanomaterials, which we have both N and P type, and you can compute, fabricate CMOS kind of structures. Putting these two parameters, material as well as printed technologies into perspective, the two important parameters what we are looking in this talk to achieve high FT, which is the transient frequency, is the mobility, mu effective, as well as the channel length. And when I put qualitatively into perspective, neglecting the parasitic capacitance, these are some of the numbers we can achieve using these materials. So if we use organic, we can push the limit to up to a megahertz, tens of megahertz. If we use metal oxide, we can push the limit to a few hundred megahertz. And then if you have inorganic nanomaterials or carbon nanotubes, we can reach up to gigahertz theoretically. With the channel length of around 1 to 5 micrometer. Also, another concern which I mentioned in the previous slide for silicon-based electronic is the growing electronic waste issue. So in the early decades, we have only seen the materials in terms of performance, not in terms of sustainability. And this is the result of that. So now is the time we need to choose materials very carefully to bring another electronic form, so that once its usage is done, after its end of use, they should not create a problem to the environment. And in this respect, a transient form of electronics has emerged where the materials chosen are eco-friendly, and they can be degraded in a controlled way. And once they are degraded, the byproducts are eco-friendly. And if we can use printing technologies to print such materials, we can form a printed transient form of electronics, which from the starting to its end can bring sustainability in the manufacturing chain. So that the summary of the slide of the talk, mainly how we can bring or use electronic responsibly starting from the raw materials. So the raw materials eco-friendly in the sense they should be abundant. And once they are degraded, should not cause any harm to the environment. And once they are into the manufacturing chain, we should have manufacturing processes which are resource efficient, should use less water, less energy, and so on. And after its end of its life, once they are degraded, the material degraded should be degradable or even compostable. So compostable can help rather than even making a problem, can have a positive impact on your environment. Or some of the material can be recycled and recovered and put back into the manufacturing chain. So in this talk from now, you will learn how printed techniques, the new printing techniques we have developed to form high mobility electronic layers, to form high performance flexible electronics. I will also show some near lithography free printing techniques where we are trying to avoid as much as we can lithography, which is very wasteful processes in the semiconductor manufacturing. And I will show you a few examples of flexible and transient devices we have fabricated, sensors and transistors, and I'll conclude the lecture in the end. So before I begin with the printing techniques we have developed to print these inorganic materials, it's this one slide summarizing quickly to the synthesis of nanomaterial. Sorry, this is an animation, but I think there is a problem in playing. So anyway, so we are exploring bottom-up approach such as CVD-based VLS growth of nanowires, where we have this gold catalyst and we bring the vapors and we are growing silicon or zinc oxide nanowires from bottom-up approach. In the top-down approach, we are starting with the bulk wafers, mainly as for nanowires, we are using bulk silicon wafers, and using a maze process, which is metal-assisted chemical etching, we are carving out some 1D materials. And there's other kind of nanostructures we are fabricating, which are nanoribbons. Unlike nanowires, which are vertically aligned, these are laterally aligned onto the wafers. And in this, we are using lithography and chemical etching and so on to make silicon wires and ribbon. So once it's fabricated, how do you transfer from rigid wafers to the flexible substrate or transient substrates? So I'm sure you have, all of you have used this stamping technique to make stamps in your life. And this is the same principle. The first technique is based on a transfer printing. So in the stamping here, you have defined your structure onto the stamp. However, in transfer printing, you defined your inorganic structures onto the ink itself. So for example, if you see in this slide here, we have fabricated this laterally aligned structures of nanoribbons, which are suspended and anchored at the end. And we bring a PDMS stamp to pick them, and then you can place it wherever you want onto the flexible substrate. So you need to play with the interface structure of the receiver, donor, and the ink. So this approach has been used a lot in the literature, and but there are some drawbacks of this technique, such as it's a two-step process, and the yield of the process is low, uh, uh, while printing nanostructure particularly. So we have developed direct roll printing. The direct roll printing has advantage. It's a roll compatible approach. In this, what we have done is that we have used a semi-cured polyimide onto the roller, and these nanostructures are defined onto the rigid donor substrates. And when we roll, because of the semi-cured nature, an adhesion is formed between the nanostructure and the flexible substrate, and we can directly print the nanostructure in one step. We have demonstrated to transfer on variety of substrates from flexible polyimides to foils, metal foils, PETs, aluminum magnesium foil. One can argue because of the semi-pure nature, there is a chance to bring impurities onto the nanostructures, but we have optimized the process and show that the nanostructure transferred are clean without any impurities. And the yield of the process is dependent on the force applied during the rolling process. And we can reach up to 95% when we apply around 12 Newton of forces. The video here shows the process. So here is the donor. We are rolling the receiver onto it. So once the receiver and donor are in firm contact, with force applied and just picked, and now the nanostructures are transferred onto the flexible substrate. So it's as you see, it's a single step, and it is very straightforward process. And the other technique we are developing is a contact printing setup. So contact printing is normally used for printing of vertically aligned nanostructures, unlike the direct roll printing, which print laterally aligned structures. This printing technique is based on shear forces between the donor and receiver. So here you can see in the printing mechanism, we have a donor, we bring in the conformal contact with the receiver, and once the forces are applied to have this conformal contact, we have a sliding force in this direction, and the wires are printed laterally onto the receiver substrates. And these are some of the SEM image you can see over a large area, how the electronic layers are formed of this inorganic material. This is zinc oxide. This is again a video showing how easy is this. So you bring here this donor and receiver in contact, and now the sliding force is able to transfer the nanowires onto the receiver. Okay, so I have shown two techniques where we are using some kind of lithography technique to have a patterned electronic layer. For example, in the direct roll, we are using lithography each time while fabricating the nanostructures. And also for contact printing, if you want to have a selective printing, for instance, here you can see that the electronic layer is everywhere. So if you want selective locations, you need to do lithography, and then you bring again the same process you can carry out, and the nanowires will be printed where there is an opening by lithography have been done. So how we can avoid lithography? There are two techniques we are exploring currently. One is in tandem contact transfer. So we can combine contact printing and transfer printing. And then there is a selective removal as well. So I'll just briefly show these two techniques. So transfer printing, as I told, we have a bulk wafer. You do lithography, and then you bring your stamp and pick and place. In tandem contact transfer, what are the advantages? That you can use more wide variety of nanomaterials. So for example, the bottom-up grown materials can also be used in this approach. So first you make an electronic layer, for example, by contact printing, as I showed, it's all over the area. And then you can bring a stamp made by standard molding process to pick and place selectively wherever you want. In this case, the lithography will be only done one time to make the master mold, to have a master template, and then the stamp can be fabricated without lithography every time using that master template. So that's the advantage of in-tandem contact transfer printing. These are some of the characteristics I just highlighted. That is a lithography free, reusable stamps. Wide range of nanomaterial can be printed using this approach, and diverse substrate compatibility, transient, rigid, flexible, wherever you want to put your PDMS stamp, you can transfer them. It's a low cost room temperature process, and it's also a scalable approach. That's some of the optical images showing the working of this approach. So we have this nanowire grown, then we do contact printing to have uniformly all over area, and then we have we bring the stamp. As you can see, these are the pillars onto the stamp where we are picking the wires and not on the around this area, and then you can make this kind of arrays of nanowires printed. In the selective removal, it's a reverse of that. So once you print everywhere, if you can remove the wires rather than pick and place, so that will give you a higher yield. In terms of yield, it's better, this technique. Then you bring a PDMS stamp which have grooves rather than pillars, and the area which have grooves the wires remain, and rest can be removed from the substrate. This is the process steps for this. We have a mold and the master template, and then you make your PDMS stamp from this. You have this printed wires, you contact, you make electronic wear, and you remove it. In terms of results, this is the SEM image showing before and after removal of the wires, showing that the alignment of wires have not changed. Well, in the PDMS, for example, it's expected that the nanowires direction could be disturbed while removing these wires, but the figure here, we have confirmed that it remained more or less aligned in the same manner. We have also done some other form of figure of merit to calculate, for instance, the density of in the positive area. Positive area is defined where the nanowire should remain, which is around 69%. And we have also done another figure of merit, which is comparing how much the wires have been removed from the outside and inside area, which is around 93%. Okay, so now after going through these printing techniques, how to make electronic layers, I will show you some few device examples where we have used these electronic layers to fabricate sensors and transistors on flexible and transient substrates. Before I start that, let's see what is the wish list to have the high performance printed transistor. First thing, as I mentioned, we should have material with high mobility. So we have shown that we can print inorganic materials of silicon and zinc oxide. The second should be the dielectric. It should conformably deposit it over these inorganic nanomaterials to have higher capacitance, minimal defects at the interface, and so on. And once you print the metal, they should form ohmic contact with the source and drain. We should have scaled down a miniaturized channel length. It should be able to deposit, and a good adhesion with the target device substrate, and mechanically robust. This is the first example where we have used direct roll printing to fabricate field effect transistors of both N and P channel. So this is the step one. Here we have fabricated the nanoribbon. We have used our roll printing approach to print them onto the flexible substrates. And then we have used a room temperature process to deposit dielectric as well as source, drain, and gate metal electrodes. The performance is shown on the right here. For example, the B here on the top right is the output scan showing an ohmic contact formed between the source and drain, which is ideal to have the efficient charge transport. And you can see the nice saturation at the end, showing the nice coupling with the gate at the channel. This is the transfer curve for a typical N channel. And this is the transfer curve at various drain voltages. If the performance extracted from these transfer characteristics, this is the summary of both P and NMOS. We can reach device mobility of around 600 for N channel and 100 for P channel devices. Threshold voltages are in positive for NMOS, which is good for normally of devices, and in the PMOS it's the negative side. On-off ratio is around more than 10 raised to the power 4 for both of the devices. Here is a typical output scan shown for NMOS and PMOS devices. A typical transfer curve combining both the devices and devices under bending. So here you can see transfer curve, which is negligible change in performance when bent in compressive or tensile strain, showing the robustness of these flexible devices. We have used, in the previous example, we have used conventional or lithography-based approach to fabricate source, drain, and gate, and we are trying to avoid, even during the fabrication, lithography. And so what we have done in this study is that we have used a drop-on-demand printer. It's a electro-hydrodynamic based printer, which can print ideally with the resolution of 1 micrometer line from SIJ company. So in the step one, we have used our roll approach to print nanoribbons. Then it goes into the dielectric deposition, which is again at room temperature, silicon nitride. And then we bring our source, drain, and for gate electrode and encapsulation our drop-on-demand printer. This is a typical device, how it looks. So we have these nanoribbons, the gate electrode and source and drain printed, and typical electrical characterization performed, output scan, and some transfer scan for both P and N type devices. In this case, the performance is, of course, not as great as conventionally fabricated electrode devices. I have shown there the mobility of N channel is around 600, which is closer to what we get from silicon electronics. In this case, the mobility reduced to around 15 to 20 because of extra contact resistance coming between source and drain as the electrode are deposited at room temperature and through printing. So there's a lot to improve in terms of increasing the device mobility for all printed devices. So detailed characterization under mechanical bending we have performed and extracted the key performance parameter of transistors. I've not shown the transfer scan under bending, but these are the extracted parameters in terms of on-off ratio, which remains quite stable for up to 10,000 bending cycles at different bending radius. And SS value showed some change. Might be because of the dielectric cracks or interface issues. Otherwise, mobility remains quite stable for these devices. this is the example where we have fabricated an N-channel transistor on biodegradable substrates, which is magnesium in this case. So we have used direct printing approach. So we have this semi-cured polyimide and we bring a conformal contact our fabricated ribbons, and this is how we transferred, as I mentioned earlier. And then the similar fabrication approach can be followed to fabricate these transistors. Interestingly, the performance on such novel metal foils or substrate, performance-wise, it remains intact. We can reach as close as what I have shown on flexible devices. This is a typical how the device looks on the magnesium substrate. Transfer and output scan showing nice ohmic contact and gate coupling, and reaching to the in a milliamp of current and transconductance in millisiemens, which is very impressive in terms of the state of the art. So this is the table which compares other devices fabricated on biodegradable substrates. People have explored PLGA silks, and in our case, we have done on magnesium. This is the long-term cycle stability test we have done. So at least, so this can be degrade, yes, but till its life, the device should be stable. So this is a attempt to test the stability of these devices. So we have done up to 3,400 cycles forward and reverse. Very less hysteresis we found, and as you can see, the performance remains quite intact. So these are the expected parameters on-off ratio, SS, and hysteresis up to all these cycles, and they are stable during the operation of these devices. So once we have done those stability tests, continuous cycle test, we have also done some bias stress on these devices, applying a positive and both negative bias stress, as well as we have done at different temperature. The scans are showing less influence of the temperature onto the transfer characteristic. At the end, we see the slow transients of the devices. We put in around pH of the body fluid, 7.4. In this case, if I remember well, but we have also done at different pH, the degradation rate of magnesium foil. As you can see in this graph, we have extracted the number, and these are the optical images of the devices under dissolution or degradation. Coming to another example, we have fabricated some high-speed gallium arsenide-based photodetectors using direct roll printing onto the flexible substrates. And the advantage of these gallium arsenide-based is that they are wide-range photodetector. They respond in from UV to infrared light. In this case, the gallium arsenide are fabricated from the bulk wafers, not from the soy wafer like the silicon case. And this is the shape of the fabricated ribbons. And this is how we have looked like after transfer printing. And then we deposit our source and drain metal for these gallium arsenide wires. A few characteristics we have on this slide for under UV light sensing. The interesting parameter is the response speed of the sensors, which was in milliseconds, and also the recovery time. It was quite fast, and the responsivity of these devices can reach up to 10 to the power 4 ampere per watt. We have also tested them under bending and twisting and showing the robustness of these devices. So these are the responsivity and detectivity plotted with the bending cycles, and up to 500 cycles, which we have used such equipment to put our devices on a different radius of curvature of the rollers and twisting angles. We have shown that, yes, the devices are quite stable under bending condition or twisting conditions. Coming to another type of UV sensor, this is all printed UV sensors. So there the electronic layer are developed using the in tandem approach, so selectively, and then we bring our super inkjet printer to print source and drain electrodes on it, and then we have done some UV characterization, electrical characterization. So this is a two terminal showing rectifying behavior with ZNO and gold, which is expected. Under UV, different UV light, as you can see, this is the time with the time and current. Under increasing the UV light, the on current is increasing, and this is some repeat of the cycles we have done at bias voltage of 1. Extracted responsivity was impressive. Here we have compared with this most of the printed and non-printed state of the art, and the peak responsivity we could achieve under very low light intensity was impressive in this case. The process was moved to biodegradable substrates. Here we have fabricated again on the magnesium substrate. So we take the magnesium foil, we passivate first using silicon oxide, we transfer zinc oxide nanowire using in tandem approach, and then we bring our printer to print gold electrodes on it. Similar characterization with the different drain voltages, and these are at different UV intensities. Extracted responsivity was quite similar to what we got on flexible substrate, showing that the nanomaterial transferred and the process what we are following is remaining same onto the different substrates. This is the comparison table. So we have fabricated similar device using conventional fabrication approach. So we deposited titanium and gold electrode. This is through EHD on flexible and transient substrates. These are the numbers for detectivity and responsivity, on-off ratio, and response and recovery times. In terms of responsivity, of course, conventional was better because of the higher or efficient current transport at the metal semiconductor interface. But because the dark current was higher as well, the on-off ratio was poor. And also it takes long time to respond and to recover compared to the printing. In printing, responsivity is okay, a bit lower than the conventionally made, but in terms of on-off ratio was better than the conventionally made because of the rectifying contacts you get at the metal semiconductor interface or for the nanowire and the printed gold. And then we tested its degradation around pH 6, temperature 20 degrees Celsius, and we see that how these layers start to disintegrate and degrade with time. Okay, so this brings me to the summary of this lecture. So the key takeaways you can see here. So first, I have shown that high performance flexible electronic anti-skin, some basics, and how you can achieve or bring high performance in flexible electronics. Where I have also shown how electronics manufacturing can be responsibly done while maintaining the power of conventional electronics. I have introduced you to some new printing techniques, which is direct roll, in tandem contact printing, and how this technique can be used to print high mobility electronic layer on variety of substrates. Some lithography pre-printing techniques I have also introduced, showing the potential that the lithography technique can be avoided completely for printing such material. And also a few examples of flexible transistors and sensors on flexible and transient substrates. This slide showing the perspective of our approach. So once these technique you can scale up contact transfer printing or other printing techniques we can bring more and more functionality to our electronics by printing a variety of nanoscale, microscale, or macroscale structures. We can also do some 3D integration using these printing techniques to fabricate large area, flexible and bendable electronics for future. In terms of using conventional printers, this is the graph showing the featured width or the resolution in the X, and on the Y, the height of the features. Till now, this is what we have explored mainly. And this is, I think, one of the reasons why we are not getting performance near to the silicon electronics. And in the coming years, I would say the opportunity lies using such printers, super inkjet, reverse offset, or even direct writing, which can bring you resolution of 1 or sub micrometer as well. And this is the area what we are exploring currently in our group. With this, I would like to thank all the group members which have contributed into this work, and the funding agencies as well. And thank you all for your attention, and you can reach out to our group by email or through social media. These are the details, and I'm open for questions. Thank you.
Thank you very much for this very nice presentation. Great results we have already. Let me check the chat. There are some questions already. Sriya is asking about, firstly, he thanks you about the wonderful presentation. And he or her asks about the effect of temperature on 3D devices. How does higher or lower temperature affects the performance of the devices?
Okay, the temperature effect we have done for transistors. So devices, I guess you mean transistor here or sensor, I'm not sure, but I have shown in here. So this is the effect of temperature for the transient devices I'm showing, but we have also done for flexible devices, and from 5 degree to 50 degrees Celsius, they are quite stable. But of course, if you increase the temperature to more than 100, I think the thermionic emission from metal to semiconductor will increase, and then that might disturb the on current as well as threshold voltages. We have not reached that temperature. We have done near body temperature, where our electronics, we are targeting these flexible patches and all on the body. So we are not expecting a very high increase in temperature in that respect. Yeah.
Okay, thank you. Sandrine is asking about, firstly, thanks you for the nice presentation. Which UV source did you use? Do you have a degradation of the flexible substrate under UV illumination?
UV source we have, it's a commercial one. It's a 365 nanometer UV wavelength. It's a standard UV lamp we have used, we purchased, and then we have calibrated using our commercial photo this sensors we have purchased, and we calibrated with the distance. Degradation of substrates, I'm not sure. I have read, or we have even done it for polyimide. Mainly we are using Captain or polyimide substrates. This is, I cannot answer if the substrate are degrading or what, in how much the rate of degradation. No, I cannot answer this one.
Okay, another question about the durability and the reliability of printed transient electronic devices, and if you can overcome these issues to meet practical applications.
Yeah, this is, I mean, is a problem, yes, and we are trying to characterize, as you see, very in depth, for example, here. So Conventional, if you have conventional electrode, the problem may not be that much because the adhesion of the electrode is good onto the substrate compared to the printed one. So printed one can have issues such as delamination of the electrodes or other layers. And in this case, we reached up to the bending radius of 15 millimeter, which is again not some have done around 5 millimeter. But the performance, as I said, the device performance varies, but it's not as significant that cannot be compensated through circuits design, So the initial test, I would say they look robust, this approach. But yes, encapsulation techniques such as optimized plasma to have good adhesion, then encapsulation, which can bring the active layers into the neutral plane, so where it is experiencing less strain. These are the approaches I think we should do it, and that can improve the robustness of these devices.
Okay, thank you. Another question: which devices perform better? These that are based on top-down or bottom-up grown, I guess, nanowires or devices.
So top-down perform better. There is a reason for that. So the one I have shown bottom up is zinc oxide wires, which again the bulk mobility is way lower than silicon devices, which we have fabricated through top-down. But we have also tested some bottom-up silicon, and in again that case top-down is better. The reason is that we are doping source and drain to make them N-channel or P-channel, and the doping is helping to make better semiconductor metal contact because you are making your metal connection onto the doped part of the ribbon. So doped part is like a degenerate semiconductor which acts as a metal, so you are forming between metal and metal. So once you form a good ohmic junctions, your charge transport is efficient, you have less losses at the interface, and that's why the performance is better for top-down approach materials.
Okay, thank you. Another question from Jessica: is it possible to use the stamp lifting method on nano nets? What is nano nets?
Nano nets, I assume you mean a mesh.
Nano network. Yes.
Nano network. I would not say yes because for stamping you need something suspended and which are anchored at the end and anchored in a very softer way so that you can break them during the lifting of the PDM stem. I'm not sure the anchoring of nanonets at the end, how big they are, because larger they are, it's difficult to pick them and without breaking them. So I'm not very sure we can use for nanonets.
Okay, thank you. Another question from the audience. You can speak or write. Meantime, I have a question about this technique, the contact transfer printing, the CTP. I mean, about the throughput and the yield of, let's say, operational devices at the end, and if it's industrial compatible with, let's say, upscale production.
Currently, yes, this is a two-step process and it has a very poor yield. So for example, if you see the density of wire onto the printed area, the yield is lower. So for example, in the beginning, in the contact printed, if you see the density you can transfer, it's quite high, right? And once you are using this approach, you are only able to print 10 to 20 nanowires in 100 by 100 micrometer area. So yes, the yield is lower. Currently, we need to work onto that aspect. The throughput is also currently, because it's a batch to batch process, is low. But we are thinking to put this approach in a roll compatible way. So you have these stamps onto a roller, PDM stamp rolled, and then you can pass your belt and do the process. So in that way, we can think of increasing the throughput. But for efficiency to improve, yes, we need to work more on the science part. And your question on to the devices, can you repeat? The reliability, did you ask?
No, just the throughput and the yield.
Okay.
These were the
Yeah.
questions.
So yeah. So they are not. I would not say they are very great at this point, but yes, there is a room to improve. Sure.
Okay, at some point you mentioned about mobility values, 600 centimeters square per volt per second. This is for, I guess this is for zinc oxide, but top down. Am I correct?
No, 600 is from silicon and top down.
And the 100 value is for zinc oxide top down.
No, 100 is for P-channel devices from silicon.
Silicon.
Yes, both are silicon is N and P, and for zinc oxide we are getting around 50. If we have characterized like 1,000 devices on a chip for ZNO, and we average is around 50.
Okay, thank you. I can see another question in the chat. It's better to let the applicants to ask. Guillermo is asking, what is the removal efficiency of nanowires? Do you have any shorts in the devices due to leftover nanowires?
Shorts, you mean shorting? These are
you presented a reverse technique that you remove the material instead of patterning.
Yes.
So I think
Yes,
he's asking about that.
Yes, the efficiency, I think you can follow the paper, but this is the numbers, what I can recall. So these are the two parameters what we are looking for. So C nanowire, I guess, is the percentage what you mean here, which is around 93%. We can remove. So that's how we are calculating the kind of efficiency, that it's a 93% efficiency. But
very high value.
honestly, I would suggest you to go through this paper, and you can read more onto the efficiency part.
Great. Thank you for the reply. Is there any other question in the audience? I have a last question about the super inkjet printing technology. I have read also some papers on that. I think they claim that they can go down well below 1 micrometer, down to nanometers. What do you think about this technology?
I think they claim, the company claim around 1, but yes, it can go with very proper optimization. We have not able to achieve. We have achieved up to 1 micrometer line, as well as the pitch, which is not for transistor but for temperature sensor work. On vanadium pentoxide nanowires, we have done that. Yes, it has potential, and it's a good tool for R&D, as you can just change the design on the go. Just to add with, to give you more on these kind of printers, there is a new printer from Humming company in Paris. They are making Nazca tool, which they are claiming can go up to 300 nanometer to 500 nanometer, which is, I think, I heard the best in the market, which is based on different technology than EHD. And then there is an XTPL company in Poland who also making this drop on demand, which can also reach up to 1 micron. But below 1 micron, my experience is that it is still not very repeatable. Yes, you can reach, but repeatability is an issue.
Okay, yesterday we had a talk from VTT on reverse offset printing. They showed some data below 1 micron, half a micron. Okay, so is there any other question? Otherwise, I would like to thank you for your participation in the school.
Welcome.
So, and with this is the last webinar of the day. So I would like to thank everybody, and let's meet together tomorrow, the last day of the school. Thank you. Bye-bye, everybody.